Okay guys, in this video lesson we're going to get down to how we quantify equilibrium using those equilibrium expressions that we first introduced in our last video lesson. Okay, so first thing, a little review. If we're trying to find the equilibrium expression or the equilibrium constant, we know we're taking the concentration of products divided by the concentration of our reactants. Okay, so that equilibrium constant, remember, is just a ratio of the two things as you do this. Now, make a note, this is the concentration of your products to the concentration of your reactants at that equilibrium. Now, what that means is we only can work with things that are dealing with concentrations, okay? And that's going to kind of play a role as we kind of start building up our expressions. So when we do this, we need to take a look at a balanced chemical equation, and we need to build an expression. We call this an equilibrium expression, not a formula, because it changes. Now, for example, PIVNERT, it's always that. MCAT is always that. They don't modify or change if you're trying to solve for energy or trying to solve for volume or pressure for gases. However, when it comes to equilibriums, they're all dependent on the balanced chemical equation and what is there. Okay, so the way we do this is our KEQ, or our equilibrium constant, will be equal to our products over our reactants. If you have more than one product, you multiply them together. You multiply their concentration again together, raised to whatever the exponent is for the coefficient. All right. This part here is important because if this is 2 or this is a 3, that changes these values in here. Again, we're not adding, we're multiplying. All right, and then that's always over your reactants in the same idea. Okay, so the brackets, now sometimes students are like, oh, can I just use parentheses here? Do I need to have brackets here? Does it really make a difference? And actually it does. The brackets themselves have a symbolism for us in chemistry. That bracket means concentration. Okay, what's nice about it is the concentration could be parts per million, it could be molarity, it could be molality, it could be percent by mass. It doesn't matter what concentration we're using because it's concentration divided by concentration. But that bracket is symbolizing, hey, it's a concentration here. It's not just some random number. Okay. So yeah, when you build these, you have to have the brackets. That is part of our kind of requirements to do that. And then you want your products over your reactants. Okay. So let's take a look at kind of a scenario here and how we could actually solve for one of these. If we have N2O4, which is a colorless gas, and NO2, a dark brown gas, if they exist at equilibrium with each other, we have this type of expression where we have N2O4 and making 2 NO2s. Okay. So our first step here is to actually write up the equilibrium expression. Okay. And to do that, so we know that if we have KEQ, and that's going to solve for our products over our reactants. Okay. And we only have one product here. So our product is NO2. And we want the concentration of that. And because there's a 2 in the balanced equation, we want to square that value. That's going to be over our N2O4 concentration. And there's only one of those in the balanced equation, so that's a 1. Again, this is optional. You don't have to write that 1 in if you don't want to. I put it there, just reminds me that I actually checked it to make sure. Okay. Now that we have this, we then can solve our problem. So if we have that KEQ, and from our problem, if we read the actual problem here, we have a liter of gas mixture at equilibrium contains 0.0045 moles of this and 0.030 moles of that. Okay, so it's a liter of gas. So again, we need concentrations here. So the 0.0045 and the 0.030 are moles. But we want concentrations. Now the nice thing is about gases are volume dependent. So if we're taking a look at this, if we have, a 1 liter container, and in that container we have the 0.030 and the 0.0045 values, okay, they're going to be mixed together inside this container. So they're both going to be 0.0045 moles per liter, or 0.300 moles per liter, because we have a 1 liter container. The beauty is, if this was a much smaller container, the volume would change to say to 0.1 liter. The ratio would stay the same. So we really don't need to worry too much about the size of the container here. we can just use our values for moles because that relationship or that ratio will hold because they both have to be in the same container anyway. Okay, so knowing that, what we're able to do is say, well, the NO2 is 0.030, and we want to square that, and we have 0.0045 concentration, and if we put those two together, then we get an answer of 0.20, and now so there is no label here because we do not have units on this because it's concentration divided by concentration. So there's no label here, okay? That brings us into this idea of what happens when we have things that are not concentrations, all right? So typically when we're dealing with stuff, we want to have things that are in concentration. Equilibriums are based off of concentrations. So there are only 2 of our 4 states of matter that actually can build concentrations, okay? So if we take a look at it, we have our solids, we have our liquids, we have our solutions, and we have our gases, okay? Of these 4, if we change volume, gases don't care. Okay, so they have no concentrations. Liquids are the same. Okay, so both solids and liquids do not play a role in concentrations. You can't have a concentration of a solid. You don't have a concentration of a liquid because they have set volumes. However, solutions, we always dissolve some sort of solute into a certain volume of a solvent, so they are always concentrations. So yes, solutions play a role here. Gases are a little bit harder to visualize, but they also are concentrations. And if you think about it, if you take a certain number of moles, let's say we have 0.005 moles of a gas, that volume has to be, or sorry, that amount has to be in some sort of volume. Okay, gases expand to fill their containers. So that 0.5 moles, you could put it in a 1 liter container, or you could put it in a 2 liter container, or you could put it in, a 3 liter container. And each time you change the container size, you would change its concentration. So it's moles per 1, moles per 2, moles per 3. So for gases, they also form a concentration. So when we look at our equilibriums, only things that are solutions or gases are things that we actually include in the equilibrium. All right, which means an equation like this, calcium carbonate solid making calcium oxide solid and carbon dioxide gas. When we write the expression, we're going to remove the solids from this. So the only thing that plays a role is the carbon dioxide here. Okay, so the take-home message is if you have solids or liquids in your balanced equations, you do not include them. Again, do not include them in the equilibrium expression because they're not concentrations, so they cannot be part of the equilibrium. Equilibriums are based off of gases and solutions only. Okay, so here are 3 different balanced chemical equations. What we want to do is test our knowledge now and actually try them out. Okay, you've seen me do one. We've talked about them, so now it's your turn. So taking this equation, barium chloride solution with sodium sulfate solution, making sodium chloride solution, and barium chloride solid, write the expression for that. Once you've done that one, do this one and do this one, and then we will show you the answers here shortly. Okay, so pause the video here and then work it out. Okay, so assuming you paused it, you have 3 answers on your sheets now. And if we take a look, here's our first one. We need to square the sodium chloride because it is doubled in our equation. We do not include the barium sulfate, because that is a solid. There's no plus sign between them, and we had brackets on that. The second one, these are both solids, so they don't play a role, so it's only the oxygen that plays a role here. And the third one, again, very similar to the first one, the water is a liquid, so it's not playing a role here. In this case, we had 2 sodium hydroxides, so we only had to square the sodium hydroxide in this expression. Okay? Once we can write the expressions, then we can solve. So the next step here is actually solving for numerical values. So here are 2 practice problems that you can do also for solving. Okay? You'll note the temperatures in both of these. It has nothing to do with your math, but because equilibriums are temperature dependent, we include temperature in our data. Okay, so solve both of these. The second one's a little harder. Use the hint to help you with that one. And then once you've solved them, again, unpause the video and yeah, I'll show you the solutions. Okay, so assuming that we've worked these out, here's our first one. We knew that our balanced equation needed 2 hydrogen iodide gases in that. So here's our expression. We plugged in the values at equilibrium, okay? We didn't care that you put 1 mole in to start. We only care about things at equilibrium here. So here's our values at equilibrium, and we get a value of 0.50. No label. The decimal point is here because we had 2 significant figures. The second one's a little bit more challenging. You had to realize that if you make 4 moles of chlorine gas, because it's a 1-to-1 mole ratio in your balanced equation, that you would also make 4 moles of the bromine. So as a result, you end up having your equilibrium expression first. We're solving for the concentration of the bromine chloride gas. So we rearrange it, and we need to do the square root of this now. 4 for each of these divided by the K expression written in the problem. The value written in the problem, 6.25, and we get 1.60 molar. Now notice, this is a molarity here, and I can write it as a molarity because it is a concentration, because we're solving for concentration, because we had 1 liter container. So if you solve this and you got an answer of 1.60 moles, that is true, but the concentration is the moles per your volume. It happened to be 1, so it was 1.60 divided by 1 for a molarity of that. If you had this in a half-liter container, your answer would have been 1.60 divided by 0.5, or basically you would have got a molarity of 3.20 molarity for this answer. Okay, those are a couple practice problems, guys. There is a worksheet in our notes, in our student files that has additional practice problems for you guys for this also. Thank you.